Last time we ended on this problem, we wanted to determine the null space of this matrix. We said that the null space was the set of vectors x in R4, such that this matrix A times x is equal to the 2 by 1, 0 vector. How we found the null space is we made this augmented matrix that consisted of the matrix A in a column of zeros. We put this matrix into reduced row echelon form and solved for the pivots. And then here we substituted R and S for x2 and x3. And then we wrote the null space in this form. Now make sure you write down this null space because we're going to use it later. Okay, let's switch gears. Let's say that V is a vector space. And we have some vectors in this vector space V. And these vectors are V sub 1, V sub 2, all the way to V sub k. And let's also just pick some scalars. Let's pick k scalars. Then we can write a sum involving the scalars and the vectors, like so. Alpha 1 times V1 plus alpha 2 V2 all the way to alpha k Vk. And this is a linear combination of those vectors in V. So when we have a sum like this, we call this sum a linear combination of the vectors in V. I want you to note that linear combinations of vectors belong to the vector space V, and that's because our vector space is closed under vector addition. So all linear combinations involving as many vectors as you want from the vector space V is going to be in the vector space. Now suppose we call W the set of vectors. So we say W is V1, V2, all the way to Vk. We're going to use some new terminology. We're going to say that the span of W, which you could also write this way, the span of the vectors V1 through Vk, that is the set of all linear combinations of the vectors in W. Let me give you an example. Let's say we're working with R3. And we know R3 looks like vectors x1, x2, x3, where these x1, x2, x3 belong to R. And let's say we pick two vectors to belong to W. I'm going to say 1, 1, 0 and 0, 5, 0. Then the span of W is all linear combinations of these vectors. So it would look like R times 1, 1, 0 or let's use the alpha 1 that we used before. So alpha 1 times 1, 1, 0 plus alpha 2 times 0, 5, 0, such that alpha 1 and alpha 2 are scalars. So an example of a vector that belongs to the span of W would be 1 times 1, 1, 0 plus 2 times 0, 5, 0. These are real numbers. So this would be 1, 11, 0. This would be a vector inside the span of W. Now this doesn't contain all vectors in R3. For example, the vector 0, 0, 1. There's no way to get the vector 0, 0, 1 in this span. So here I have a claim. The claim says that the span of W is a subspace of our vector space V. Let's prove this. Well, to prove that it's a subspace, the first thing we need to ask ourselves is it a non-empty subset of V? Well, obviously it is a subset because we have linear combinations of vectors in V, and we said that such linear combinations belong to the vector space V. We need to make sure it's non-empty, and we can show that the zero vector belongs to the span of W. Why is that? Well, remember W is a bunch of vectors in V, and the span of W is all linear combinations of vectors in W. So this linear combination, 0v1 plus 0v2, all the way to 0vk. Here we have alpha 1, alpha 2, all the way to alpha k. They're equal to 0. This is a linear combination, and it's equal to 0. So then, because it's a linear combination, it belongs to not W, but the span of W. So that's the first thing you need to check. The second thing you need to check, you can do it really in whatever order, but you need to show that if alpha belongs to the real numbers and W belongs to the span of W. In fact, I want to use a different letter than alpha. Let's call it, let's use sigma. So if sigma is a real number and W is in the span of W, so W, we're labeling that as a vector, then we want to show that the span of W is closed under scalar multiplication. So then is sigma times W in the span of W. To show this, we need to see if sigma times W is a linear combination of the vectors in W. So to answer this, is sigma W a linear combination of vectors in W? Well, let's see. Since W belongs to the span of capital W, then W is a linear combination, so it's alpha 1 V1 plus alpha 2 V2 all the way to alpha k Vk for some alpha 1, alpha 2, alpha k scalars. And then sigma times W is going to be sigma times alpha 1 V1 plus alpha 2 V2 all the way to alpha k Vk. This sigma, remember, part of the rules of a vector space is if you have a sum of vectors and they're being multiplied on the outside by a scalar, you can send that scalar into everything. It distributes. So this is sigma alpha 1 V1 plus sigma alpha 2 V2 all the way to sigma alpha k Vk. I'll put parentheses around this. And notice that each one of these is a real number. And now we have all of the vectors in W, and they're being multiplied by scalars in the real numbers. So this is a linear combination of vectors in W. So that implies sigma times W belongs to the span of capital W. So we have one more thing to check, and that is if the span of W is closed under addition. So number 3, if W and let's say Z belong to the span of W, does W plus Z belong to the span of W? Well, since W and Z belong to the span of W, we can write them as linear combinations of the vectors in W. So this is alpha 1 V1 plus alpha 2 V2 all the way to alpha K VK. And now we're going to say Z is beta 1 V1 plus beta 2 V2 all the way to beta K VK. Now if we add W and Z together, we'll get alpha 1 plus beta 1 V1, alpha 2 plus beta 2 V2, all the way to alpha K plus beta K VK. But notice that these sums belong to the real numbers because it's a real number plus a real number. And here we have a linear combination of the vectors in W. So this implies W plus Z belongs to the span of W. And so our final conclusion is that the span of W is a subspace of V. Here's something interesting. The span of W is what we're going to call, it's basically the smallest subspace of V containing the vectors in W. So what you want to think of is you have these vectors in W and you want to make a subspace with them, but you don't want to add anything unnecessary, any other vectors that you wouldn't get from linear combinations of the vectors in W. So that's what we mean by smallest subspace. All right, let's say that V is a vector space, and suppose there exists vectors V1 through Vk such that V is the span of these vectors. So we're not, I guess you could call these W if you like, and we're saying the whole vector space V is equal to the span of W. Then we say that these vectors are a spanning set of V. Or you can say the vectors span V. So what we're saying is, given a certain amount of vectors, all linear combinations of those vectors produce the whole vector space V. I'm going to show you an example of this. Here's a claim. These three vectors span R2. Let's see if it's true. So what I'm trying to show is that R2 is equal to the span 1, 0, 0, 1, 2, 3. That means R2 can be written, any vector in R2 can be written as a scalar times this first vector, a scalar times the second vector, and a scalar times this third vector. Is that true? Well, you could do this. We could do a couple of examples by you just providing me a vector. So let's say you gave me the vector, I'll do it in a different color. Let's say you gave me the vector 7, 7. Can you write this vector as multiples of these vectors added together? Well, sure, you could say this is 7 times 1, 0, plus 7 times 0, 1, plus 0 times 2, 3. That's one way to write it, as a linear combination of these three vectors. You could also say 7, 7. let's see, let's give one of these 2 3s. So that'll be 3, so I'll need 4 0 1s. And then I'll need, so I have 2, so I'll need 5 1 zeros. So we've written it 2 ways as linear combinations of these 3 vectors. And the idea is you can do it for every single vector. And that's what we need to prove. We can't write out every single vector. There's infinitely many vectors in R2. So what we're going to do instead is we're going to let AB be a vector in R2. And let's see how we can write this vector in terms of these 3 vectors. So we want to find alpha 1, alpha 2, and alpha 3, if it's possible, such that we get AB. Now this is a system of linear equations. We have alpha 1 plus 0 alpha 2 plus 2 alpha 3 is equal to A, and then 0 alpha 1 alpha 2 plus 3 alpha 3 is equal to B. So we can form an augmented matrix to solve this. One 0 2 0 1 3 AB. But look, this matrix is already in reduced row echelon form. So we can say that alpha 1, solving for these pivots, alpha 1 is equal to A minus 2 alpha 3, and then alpha 2 is equal to B minus 3 alpha 3. So alpha 3 is our free variable. It can be anything. And then from that free variable, we get alpha 1 and alpha 2. So AB is equal to A minus 2 alpha 3 times 1 0 plus B minus 3 alpha 3 0 1 plus alpha 3 2 3. Let me make this smaller so we can see it all on, sorry about that, on one screen. Okay, so whatever you put in for alpha 3, let's say you put in 0, you'll get that AB is equal to A times this vector, B times this vector. So if you had, like we said, 7, 7, we put in 0 for this one, we'll get 7 and 7. If we chose 1 for 2, 3, like we did before when we had 7 and 7, then we would take whatever's here, if it was 7, and subtract 2, which was 5. And then we would also take, we have 1 here, B, which was 7, minus 3, which was 4, and we'd have 5, 4, 1, just like we did, I think I erased it, yeah I did, when we did 7 and 7. But here we're doing this for any A and B, so you could choose 25 and negative 13, you'll be able to figure it out. So we have infinitely many solutions for these 3 variables, alpha 1, alpha 2, alpha 3. Now if we had some vectors that did not span R2, what would happen? Well, we would get an inconsistent system. So here we had 3 variables and only 2 pivots. We had infinitely many solutions. But if we have no solution, the vectors do not span the vector space, you're going to get a row of zeros and then a non-zero number here. All right, remember I told you to write down a specific problem, the answer to a specific problem, which was to determine the null space of this matrix. I want to find a spanning set for that null space. So let's write down what the solution was. thought I had it copied, so give me just a second to copy it down. Actually, I might have it written down, so just a second. Yeah. So we said that the null space was equal to the following vectors. Negative 2r plus 3s rs0, such that r and s belong to the real numbers. Now we want to find a set of vectors. Then when we take all linear combinations of those vectors, we get the null space. And let's do that. We're going to put negative 2r plus 3s here, rs0. Notice that we can write this as r times negative 2, 1, 0, 0, plus s, 3, 0, 1, 0. Do you agree? Negative 2r plus 3s, r plus 0s, r plus s, and then 0. So this is exactly what we have here. The null space is the span of these two vectors. So now we found a spanning set being these two vectors. These two vectors, when we take the span of them, we'll get the entire null space. Let's try another problem. Let's find the subspace of R 2 by 2, so the 2 by 2 matrices, consisting of all matrices that commute with this matrix B, which is 0, 0, 1, 0. And then when we find the subspace, we want to find the spanning set as well. Okay, so when we say commute, we mean commute with respect to multiplication, because all matrices commute with respect to addition. So let's see. We want to find all matrices that commute with B. If A commutes with B, then A times B is equal to B times A. Let's define A as the matrix A, B, C, D. Then we want this property. A, B, C, D times this matrix, 0, 0, 1, 0, to equal 0, 0, 1, 0, A, B, C, D. Let's multiply the left-hand side. We get B, 0, oops. Sorry about that. Okay, so we get B0, D0 is equal to 0, 0, A, B. Okay, this tells us that B is equal to 0. Same thing here, B is equal to 0. And then we see that D is equal to A. And there's nothing that involves C, so C is free. So that tells us that A looks like this. Remember, it was A, B, C, D. Well, we have that C is free. D is equal to A, so let's erase this D and put A. And B has to be 0. So now all matrices that commute with B have this form. So let's let S be the subspace of all matrices that commute with B, which we said was, I believe, 0, 0, 1, 0. Then S is going to be equal to A0, C, A, such that A and C are real numbers. So this is one way to write the subspace. Now we've found the subspace, let's find a spanning set. Notice that A0, CA is the same thing as A times 1, 0, 0, 1 plus C times 0, 0, 1, 0. And so S is equal to the span of these two vectors, 1, 0, 0, 1, 0, 0, 1, 0. We've found the spanning set.